Yeah, thank you guys. So, yeah, I'm also a bit full after lunch. I actually stole a second sandwich, but hopefully the energy kicks in and I'll give a good talk and keep you entertained for the next 40 minutes. But I'm going to give a talk about graph databases and how you can leverage those to actually resolve security issues in your application. And this is a common issue today, where you have CI/CD pipelines running different types of tests, and we've been talking a lot about tests earlier today as well. But as we can see, we can also have security tests. And here we have one that says that you have failed because you seem to have vulnerabilities in this particular application. Well, this can be a challenge because vulnerabilities can appear seemingly out of nowhere, and maybe you have to ship this particular feature today because maybe one of your most important customers are having downtime because of your application. And security in open source is definitely not something new, but it's been something that's been emerging, and there's been a lot of talks with things such as the Biden order and some really high-profile vulnerabilities in the ecosystem of open source. Here we have a bit older one, the Heartbleed vulnerability from 2014, but just not many months ago, we had both Log4Shell and Spring4Shell. And the basics with security in open source is that you publish vulnerabilities in open security advisories. The largest one is NVD. It contains today almost 200,000 vulnerabilities. And there are about 20,000 new vulnerabilities or weaknesses in open source projects published to these databases every year. But typically those vulnerabilities are not too hard to resolve for you as a consumer of those open source projects. You simply update the project to a safe version. Sounds easy enough, but in this talk we'll go through why this can be trickier than you think. Looking at these different flaws, it takes about 800 days for an open source project to discover that they have a weakness in their code and publish a vulnerability report on that particular weakness. And updating as an end user to the safe version of that project takes about 100 days, and you're constantly about 100 days behind on the latest versions on average for open source projects. And if there happens to be a data breach, there is an average of about almost 300 days for it to actually contain that breach. And all ecosystems or programming languages are not created equally today. We can see here that the time to discover code and publish a vulnerability that has a security flaw takes quite a lot longer for ecosystems such as NPM and Maven compared to NuGet, which is C# and pip, Python, which today perform a bit better in terms of finding these security flaws in a timely manner and publishing new vulnerabilities. So this is my day. I work with this all day and every day for the past about 4 years. I was the co-founder of Debricked, which is a software composition analysis tool. We help our customers manage their open source security with the open source they consume. I head up our research and development department, but I usually do a lot of spaghetti coding when I have time as well. Open source is a graph. So when you decide to leverage the power of open source to increase the value you can bring to your end customers, you usually pick a few projects or a project that you think you can have this type of leverage with. These are your root dependencies. These are the ones that you interface with in your application layer and actually develop code with. But that's not the only open source you get. you usually get a lot of other open source projects for free without actively choosing them. These are called transitive dependencies. And they come throughout the layers of the open source community, where we can see that we have an example here of 2 root dependencies that in turn depend on some other open source dependencies, and we have this layered structure. And different communities have different depths as well. And we'll go through a bit of why this is possible in NPM to have a depth that's normal of 40 layers of dependencies, while in Python you usually only have 3, 4, 5 layers of transitive dependencies. And vulnerabilities in your open source project may not also come only from your direct dependencies. These can come from those transitive indirect dependencies as well. So in this example, we can see that we have a project called Jest of a particular version, and that in turn trickle down to a vulnerable dependency called Lodash, a very common JavaScript dependency. So this is a typical case of a transitive vulnerability. There's lots of vulnerabilities in Lodash in particular. And vulnerabilities appear, as I said, in different depths, depending on what programming language you use. So we can see here that the most shallow communities in terms of vulnerabilities are Maven and Go. So on average, Java vulnerability appears on about 2.2 depths. Where in NPM, the JavaScript package manager, we have a much deeper vulnerability on average. And I've analyzing this and playing around with the data, it's not uncommon to see a vulnerable depth of about 40 down the dependency tree for NPM. So that's quite interesting. But how do we fix these transitive vulnerabilities? Can we force update the transitive dependency? So, of course, Lodash fixed their security issue internally and released a safe version to the public to use. But you as an end user installing Jest and interfacing with that particular library, how do you make sure that that in turn trickles down to a safe version of Lodash? Well, there are functionality to usually make this force update. You can do this in NPM. But there are challenges with this that I think we should dig a bit deeper into. There's something called breaking changes. Most of you have probably experienced this some time during your career. This one was particularly nice. It broke my pipelines as well. It was the library cryptography that all of a sudden said that, okay, we're gonna need Rust for this particular dependency, and if you don't have Rust installed on your machine, then it will break. And they did this in a minor version update. So that was very nice of them. They did not. They have a different version of Semver, I think, but that makes it very hard to actually follow. So, first question: how common are breaking changes? When do things break? If we take when you release a major version, so a major version release, how common is it that you have a breaking change from the previous version, so the latest version of the last major version? Any guesses? Almost always, but that's not quite true. Do you think there's a difference in the minor version releases? So it turns out each major version release, there's about a 36% chance of breaking changes. I thought it would be higher, but I definitely thought in the minor and patch releases that it would be lower. So this is quite interesting. And there are, like, what actually breaks is actually quite, there's a pattern here as well. Usually you have method removal, class removal, or a field removal within the Maven community when when it breaks. But then there's one particular question that I think is especially interesting here that I'm wondering about, me being a data scientist and a Python developer. So what about Python? Well, Maven is actually quite good in terms of breaking changes compared to other communities. So if you look at dynamic programming languages, it's actually much, much worse. I didn't manage to find any good research on how common it is with breaking changes in Python because it's so hard to derive. You don't know what type you're essentially returning from a function. So does it break, does it not break? It's hard to know. But they could determine that it's worse than in the Maven community, so it's not great. So what we really want here to update is not to force update Lodash, because if we have breaking changes in between a patch or a minor or a major version release of Lodash, we will have those breaking changes in the interface between the dependency that's actually using Lodash. So some on core will have breaking changes in Lodash, common utils will have breaking changes in their interface to Lodash, and that's going to be really tricky for us as developers to actually fix those and manage those as time goes on. So what we want to do is that we want to update Jest to a version that in turn trickles down to a safe version of Lodash. So it turns out that this is a graph problem. And graph problems are tricky for many reasons, but they're especially tricky here as well because communities are different. We have different types of resolution algorithms for how a package manager resolves its dependencies. And they affect the community quite a lot. So I think we should do a community review here, looking at if depth matters, for instance, and also looking at if you can install multiple versions of a single dependency, and what happens if you don't have overlapping version ranges down in the tree. Will it break? Will it install more versions? Will it pick one? Which one does it pick? And so on. So let's venture into the world of ecosystems. And here we have Python. I've given them personas because I think they're kind of equivalent to the resolutions algorithms. So Python is a hipster that just turned 30. I identify a lot with this particular persona. The depth does not matter in Python. And multiple versions cannot be installed at all even when you don't have overlapping version ranges. And if there is incompatibility, meaning that the version ranges don't overlap, it will just break. It will break your pipeline or try to install different versions forever. If you're a Python developer, you probably have seen this about a year ago when they first actually released any resolution at all. Before 2020, Python did not resolve dependencies. They just picked the first one they saw, and that's how they chose which version to install. So let's have an example here. We can pretend that the pink dots can be any package, but we're actually looking at the gray dots here. So here we have two version ranges, one that's equals to or greater than 2.0, or smaller than or equals to 0.3. And here we have another version range down here of the same dependency, but it's not overlapping. So in this particular example, Python will break. You will not be able to install, it will break your pipeline, and you will have a bad day that particular day because your task will be to find root dependencies or bring transitive dependency up to the root level to find compatibility somewhere. And that's gonna be a bad day as a developer. And then we have Java. I call that the boomer, depending on because it's a resolution algorithm. Marketing said it was okay that I said boomer on the talk, but they're all millennials, so I'm not sure. But please send me complaints otherwise. But Java and Maven cannot resolve multiple versions as well. But depth does matter in its resolution algorithms. But the thing is, if you don't have overlapping, just nothing happens. What they do is that they find the most shallow occurrence of that particular package you're trying to resolve, and installs that. And even if there are multiple versions on the same depth, the resolution algorithm is to pick the one that's highest up in the POM files. So actually, maybe not a great resolution algorithm if you want to make sure that you don't get breaking changes. So in this case, we will actually install 0.3 because I picked that's highest up in the POM file for this example. But what will happen down there? Well, that's your problem. So yeah, no particular help from Maven there. Hopefully you have really, really good test coverage that tests all the edge cases down to this particular execution path. Then we come to NPM, the hippie in the party. Everything is okay here. Everything goes. And depth does not matter here either. And you can have multiple versions of the same dependency that you're looking for. And it just installs everything. Even when there's no overlapping version ranges down the dependency tree, just install everything. Which I think is a pretty interesting choice here. Because I'm not an NPM or front-end developer, but I've heard that it's pretty important with build size in your front-end applications. And it seems quite inefficient to have duplicate code over different dependencies in that for your application. Just a thought here that I haven't dug too deep into. But this means that you're always compatible. You cannot break the tree. You will not get breaking changes. And I think this is a vital part of why the NPM community has moved and thrived in such a way where you have small dependencies that are imported everywhere in different versions, and you have very, very deep dependency trees, because they won't break, and you won't have breaking changes or incompatibility in between the different nodes in the open source tree. So this enables this behavior of small projects and a lot of projects when you use open source. So this one will install both 0.3 and 0.6. And then we have the last one, the sane dictator, Golang. So Golang was partly developed by two Googlers, and it's a common story that, well, if you don't, either you have a strong consensus among a community of how you should develop a language, or you have two Googlers that spend a lot of time thinking about really hard problems and come up with quite nice solutions. So in Golang, you can actually install multiple versions of the same dependency, and that doesn't matter at all. But if you have incompatibilities, it's different, but I think it's kind of nice. So Golang always picks the largest version within a minor or patch, within any minor or patch range, but can install multiple major releases of a package. And it actually views major releases as completely different package. So v1.0 is a different package from v2.0. So you can install both of them, but it will always pick the largest occurrence down the tree. And this actually forces the community to kind of behave, because then you always have to make sure that your application or your open source project is forward compatible, which is essentially not doing breaking changes. And if it's not forward compatible, then instead you release a new major release, which enables people to use both versions without breaking changes. I think that's a quite interesting approach for this particular case. And version ranges are not a thing really. You can do it, but it's very uncommon in GoMod. So I put explicit versions here, and it will install 0.6 and 1.2 for this particular case. So let's get into the graphs. So we at Debricked, I've worked a lot with this type of problem to try to find the route that trickles down independent of the community to exactly the safe transitive dependencies you want. So we use Neo4j, which is a graph database. It's a startup or scale up at this point. I think they closed their Series B quite recently. That's open source and has a query language called Cypher. It's quite similar to any query language. It's just that it's very much focused on graphs and relations and querying multiple hops within relations of the graph. And it has a community version which is free, not as powerful, but really nice to get started and play with. And what we did is that we built a system based on a pub sub architecture. So in the center here, we have RabbitMQ, which is a broker for event-driven systems. We have a small Python application that scrapes all the different package communities to see when they release new versions. And every time they release a new version, we input that particular package into the queue. And that in turn scrapes the direct level dependencies for that particular package. So we don't build the full tree in each particular task. We just take the direct level dependency and then recursively requeue each dependency it finds. So it's a recursive algorithm to build the full graph, but it's a recursive through a queue. And in each task, we simply insert each node and its relation to its parents and children, depending on what we find in the particular data we fetch from these package managers. And I think I did sacrifice this morning. So let's see if we can show some real data from Neo4j. So this is can you see? Good. This is the interface you're met with if you interact with Neo4j and their basic deployments. We can have a look at the data model that we have. Let's ignore those. It's only these ones that I'm after. It's quite a simple data model in the end. We have a dependency, and this dependency is a particular version. So if a dependency has multiple versions, it will be unique nodes for each version. So the unique ID is the package name plus the version string in the end. And it has two relations. It has uses to go down the tree, and it has transitive off to go up the tree again, if we want to do that. We also have another node storing the version ranges of a node that this uses. So just maybe uses some version range of Lodash. Then that's stored in a version range node that connected to Jest, but the version range node is of the ID Lodash. So then we can populate parent and link to parents as well throughout as we find more nodes in the tree and traverse those. And I've picked a particular dependency here. This dependency is changelog, convention changelog here. And let's it is this one. So here, this is the exact version I'm looking at. So convention changelog 1.1.24, and if we look at the npm package manager. This is a node dependency. We can see that we have 97 versions of this particular package. And when I queried looked for all the instances we have of this dependency, of this particular package ID corresponds to this dependency, we find that we have all these 97 different occurrences in our graph. But we don't have any relations because, of course, they don't use each other in this case. But we can expand here and see and kind of get an understanding visually. So I expand this particular node here. We can see that this has some direct dependencies here. And they interact with each other as well in something that's somewhat complex. And then we can expand even further, and it gets even more complex quite fast. So let's target this particular version that we looked at. So it was 1.1.24 here. And yeah, it has quite a lot of different dependencies and some version ranges, and each node, since each node is not a version range, but one particular version of dependency, I actually have duplicate packages here, but of different versions. So all versions it could potentially resolve. That's how we have built the data model here. But we are looking for a particular path. So we have a vulnerability here in this trim new lines library. And we can see that it is vulnerable everything before 3.01 and also some versions here in the 4 major release here. And it's npm, so of course we can have multiple versions of the same library. So we get a few instances of trimlines 2.0, but also we have one instance of trimlines 1.0. So what we really want now is to find the version of conventional changelog that will resolve through all its path to a safe version of trim new lines. So let's look at the path to the vulnerability. So here we can see this is the root dependency here that we checked out. And this one is the vulnerable one, and this one is the other vulnerable version. So as we can see here, we have version 1. If you look further down to the right there, version string is 1.0.0 is one version that we are able to resolve, and then we can see we have paths to 2.0.0 as well. So the beautiful thing with Neo4j and Cypher is that you can query different depths and different jumps in this graph database. And the syntax is quite simple in the end. So looking at here, I extract a path with this match statement. I have the root dependency, and I want to query the relation uses in the direction downstream. Until I reach this vulnerable dependency, and then I've filtered on the root package needs to be this particular package ID, and I'm looking for the root version, which is this particular version string, and then I'm trying to resolve, looking at all occurrences of the vulnerable package in the end. So thinking of, can I try to use some smart filtering in how I resolve this and find the safe root dependency? Can I filter on that there is no paths to the vulnerable versions? Well, that may be possible, But if there's no paths to the vulnerable version, that means I'm probably gonna overshoot a lot when I update my root dependency, because that means there's no connection between to any of these vulnerable versions in trim new lines, and but that can of course be okay, because I just need to. It's not about there not being a connection. There's about what the package managers actually will choose in the end when they resolve the dependencies. But for fun, we can try to make such a question: is it safe? Meaning that I can have the same query, but I also filter on the version string. So here we have a representation of the version string which is padded. This is a technique to make some version strings comparable to each other, as they're not directly comparable to each other. So it's just, but it's essentially 3, 0, 1 here. So we're trying to find we're trying to see if we have any connections to versions that are larger than 3, 0, 1, which, as of this vulnerability, should be within the safe range here, as long as it's not 4, but we can check that out later. And it turns out we actually do have connections here. Here it is. But as we know that we have already tried in our scanner that we will resolve down to the vulnerable version, so this is not sufficient in actually how we mock the dependency resolution algorithm in the Graph Database. And it turns out that yes, Cypher is great, but it's also very limited. We need to have a traversal strategy. So how we search in the graph is very specific to each package manager. And we need to adapt to that problem. And we won't be able to write anything that will resolve this in pure Cypher. I actually called Neo4j and got a few of their senior engineers to help me out to try to resolve this in Cypher, and they came to the conclusion together with me that we won't be able to do this. But they do have one really, really cool feature in Neo4j, which is called procedures. So Neo4j is built using Java, and you can actually inject your own custom algorithms implemented in Java directly into the database, which is quite insane, I think. Like that feature in MySQL that's quite far away, I think. So I'm very, very happy with that feature. So you get the underlying data structure is a property graph for Neo4j, and you get direct access to the property graph and can build super efficient graph search algorithms with these procedures. In the end, I just need to set these parameters. We have built a procedure that for npm that is called getMax path vulnerable, which is if you think about how npm resolves vulnerabilities or resolves dependencies, it always resolves a max path. So traversing down the tree, and in any intersection or in any node when you decide what children to traverse, for each package that you have in that particular relation, you always just traverse the max path and you save that path. If you do that for all potential paths until you reach this package that we're targeting, the vulnerable package, if all the max paths are safe, it turns out that this is mathematically complete, that then we can guarantee that you are secure. We may overshoot a little bit in what versions we recommend at the root level, but the algorithm is much more efficient than doing it the real way and trying to agree exactly what versions will resolve. And looking at the times when we implemented this, So this one is not went quite fast. And now we're only traversing a depth of 4, but we can do 15, and it's still more or less instant. When we try to do this in Cypher, we could get query times easily up to like 4 hours in large trees, while this working directly with the property graphs with these injected algorithms essentially speeds the graph search up so much. So this is I'm testing the same version as before, and if I return a node, it deems it that we did find a path to a vulnerable node, and we will not recommend this root version as safe. But if I change the version, so now I just updated this version ID that we're testing to 3.1.10, and it does not return a node, so that's great. That means that all max paths are not returning a vulnerable version range of the vulnerable dependency that we're targeting to fix. And I can even try, I even commented in the ID that's the version before, and we can see that that then we return a node, so there is some path that may resolve the vulnerable dependency here. And looking how this would look in the, if we try to install this and make the change, this would be exactly what it would look like in the package files. So we would get the conventional change log changing to the version that the graph would recommend, and then we have the lock file. We have trim new. What was it? Trim new lines. Here some stuff was removed, and that's just a version range. And down here we see what version is resolved. So we actually get 3.0.1 exactly in the graph, which is, yeah, I think this is quite cool. I know graphs was very, very hyped a few years ago, and maybe blockchain is the thing now, but I think this is a really cool thing in terms of like what you can do with this graph technology, and it's a perfect problem for like what we're trying to solve. And we tried it out as a master thesis to begin with, and have developed it further since then. And yeah, it's been really, really fun to work with, and Neo4j is so powerful in graph traversal algorithms, especially with these procedures that you can implement virtually any custom graph algorithm you like, and traverse graphs efficiently. So thank you for listening.